So, hello everyone. I hope you've had a great evening yesterday. And today will be also a really exciting day. And we will start with the keynote lectures. And the first one will be provided by Lucjan Sajkowski from Geological Survey of New Zealand. And we will begin with this online lecture.
Victoria Wellington, coming from a centre of North Island here in Taupo. For all of you who don't know much about New Zealand, just a reminder, we are not Australian. And from Wellington to Sydney or to Australia is more or less the same distance as from Berlin to Portugal. So close, but not the same. When we talk in New Zealand about extraction of geothermal from elements from geothermal brine, we focus on critical elements. Some countries like States or European Union have got a list of critical elements. We don't have it yet in New Zealand, it's undergoing. But we define the critical elements as those that are crucial to society for economic growth and crucial for national security, and which are vulnerable to supply disruption. So when we look at the opportunities, we look at lithium, cobalt, or cesium, tellurium, or rare earths as a main point of our research. So shortly about history, it's not a new concept to extract metals from geothermal fluids. In late 50s and early 60s, there was a first study by Kennedy and others, and made by DSIR, which is a precursor of GNS. There was a heavy work in 70s on silicates and heavy metals done. And today, after me, there will be a speaker from Geothermal. Isabel will tell you more details about today's work. So we focus about the New Zealand geothermal resources. So we do have traditional resources as well of the critical elements, but in this talk I'll talk about our geothermal resources. So why do we have geothermal resources? New Zealand lies at the southwest end of a vast horseshoe-shaped zone of intense volcanism and earthquakes. We call it the Pacific Ring of Fire, and we're located here. And I'm calling from more or less here. This is a top lake, and you can see the Lucjan volcano, which we can see from our town. This is the east-west cross-section of central North Island, passing through the Lake Taupo. And what you can see is the Pacific plate submerging beneath Australian plate. The earth crust below the Taupo volcanic zone, which is here, extends from the volcano, which was in the previous photo, up to the White Island. It's a V-shaped zone. So the earth crust below the Taupo volcanic zone may be as little as 12 kilometers deep, which is very unusual and means that there is a lot of heat close to the surface. Hydrothermal activity is widespread in the North Island, which is this island. But high temperature geothermal systems are mainly restricted to Taupo volcanic zone, with one system outside in Northland. So our New Zealand geothermal system are dominated with rainwater. So this is the theory behind geothermal reservoirs. We have the rainwater traveling through our rocks towards the heat source, so the shallow magma. and then the heating takes place, and then the hotter water will travel up and interact with rocks. So mainly, the composition of geothermal brine is derived from water-rock interactions, so it depends on what rocks we have, with small input from magma. In today's New Zealand geothermal reservoirs are high temperature modern analogs of epithermal precious metal or deposits. So here again, the topovolcanic zone marked with this V-shaped like line, and where most of the active geothermal systems are, and those marked blue are the system where the current power generation takes place. And yes, you can see one system outside in Nafa. And by the way, 20% of current New Zealand power generation comes from geothermal sources. And here on this map, you can see there is many more geothermal reservoirs, but not all of them are currently in use. So for the purpose of this talk, we're going to focus on only those reservoirs where current power generation takes place, and I'll explain that later. So as you can see here, another map, mainly geothermal reservoirs which are currently used, positioned in rhyolite-dominated systems. So the rhyolite and the grey-rocky basement, those rocks are the rock which influence the chemistry. So this is a schematic section showing the geological settings of geothermal systems to around 3 kilometers depth. And they're outlining the geothermal plumes, represented by this distribution of near-neutral pH chloride waters, a yellow field. And black lines are the vertical wells which exist in current New Zealand geothermal reservoirs. So basically, all of the waters, the North, Nafa, and the topovolcanic zone, are near-neutral chloride waters, which will obviously change when you go to the surface, especially in areas where there is a lot of H2S gas, and then those become very acidic waters. So we can divide all active, currently power generating fields in New Zealand into two groups, the high gas and low gas groups. So this is one triangle where it shows the difference between chloride and CO2 content, and then chloride and H2S. So you can see that the high gas get a lot of H2S and CO2, and those are CO2 is the dominant species, whereas the low gas fields are mainly chloride dominated. And here we're talking about Rotokawa and Kawerau or Wairaki or low gas. So for a few next slides, I'll be showing you examples of the chemistry of those fields. Different New Zealand fields based on two examples of Rotokawa, which is high in gas, and Wairaki, which is low in gas. But before we will go to details, another way to show the main composition or major species composition of New Zealand brine. So as you higher the circle on the graph and bigger, that means that the concentration is higher. So you can see that those are chloride dominated waters with sodium, silica, potassium, boron, and other minor species. basically for all of those fields except Naphtha, where boron is another major component. And here another graph which shows concentrations of different elements in New Zealand geothermal brines. So each different shape will show different film, and the elements are ordered by atomic number. So you can see we've got elements around 1000 ppm in concentration, so milligrams per liter, to nanograms per liter. And as I said before, the main components are sodium chloride, silica, potassium, and boron for Naphtha. But one more thing, but as you can see, we've got whole periodic table basically in the geothermal brines of New Zealand. So what about lithium? One way of showing the concentrations of lithium in New Zealand is to just show you the milligrams per liter. So as you can see, the Mokai, which is low gas, Tauhara, which is next to Wairaki, low gas, and Wairaki, those are the three fields with the highest amount of lithium. So we're looking here between 29 and 13 for Wairaki milligrams per liter, and the lowest currently Kawerau around 6 milligrams per liter. So the higher gas reservoir have got lower lithium concentration. But I believe that's not the best way to show the concentrations of lithium in New Zealand. Why? Because if we are going to be extracting any elements, and especially in New Zealand, currently we will need to do it next to power station. So power station currently produce and reinject millions of tons of water every year. So it does make sense to open the extraction operation next to the power station. So when we look at concentration milligrams per liter, then the question is, but how many liters do we have available there? How big are those reservoirs? And then how much can we actually access of the water? So this is a little table which shows you examples of how many tons per day each of the power station is consented to produce, and how many tons per year that is. So you can see that Wairaki, for example, we are talking about 89 million tons of water every year flowing through the system. And just on the side, those numbers are consented amounts of fluid which can flow through power station. So maybe it's not that much as they use, but this is what each power station can produce each year. So that if we take those concentration milligrams per liter and multiply it per amount of fluid which each power station can produce each year, we can create this graph. So now we've got tons per year of lithium based on the consented amount of fluid which flows through power station available. So we are talking about more than 1,000 tons of lithium in Tauhara and Wairaki, and around 400 tons for Wairaki, for Mokai, and a few hundred tons for Naphtha. So we're talking here about hundreds of tons of lithium every year potentially available to be extracted in those systems. But what if we translate it per price? So it's not I know that's not the current price of lithium. When I was making the presentation, I checked it. I think it's from 2019 or 2020, but anyway, it's probably $77 now. So if we multiply the amount of lithium which can be extracted each year by the current price from each of the locations, we are talking about millions of dollars of potential lithium locked in those reservoirs, flowing through power station and being virtually reinjected back to the reservoir. So it's and reinjection is just pumping wastewater back to the reservoir. So we're pumping this wealth as a waste. So what about other elements? So here we are looking at the two systems, low gas system and high gas system, and elements on the x-axis are sorted by their value, so how many tons per year of each of elements is flowing through power station. So we've got like more than 10,000 tons of chloride or potassium in Wairaki, 100 tons of lithium, but also look, arsenic, which is used in batteries, rubidium, which is used in photovoltaic cells, tungsten, phosphorus, and even a few kilograms of gold. Rare earths, around ton a year of each. And at the high gas system, the heavy metals are much more abundant. We're looking here, for example, at 100 tons of potentially available silver and tellurium. So this is the same graph, but here I excluded few elements so you can have a better look at and compare those two systems. So first of all, the different systems in New Zealand will have different concentrations of different elements. And the high gas system has got quite a bit of gold and silver and selenium, where low gas systems full on lithium, rubidium, and germanium. And all of them got at least kilograms of rare earths. And this graph shows again Wairaki system and the Rotokawa system, but this time the values of tons of each of the element are multiplied by their price. And it's shocking how much the rubidium which there is worth. We're looking at hundreds of millions of dollars worth of rubidium. And think about this, if there was an extraction technology available which is only even 10% efficient, we are still talking about a lot of money. The valuable elements, when you look at it from this perspective, so the price and M1 is definitely germanium, lithium, gold, tungsten, silver, and definitely gold, again, rubidium and silver for Rotokawa system. So what next for us? You will hear much more about the actual active extraction operation in the next talk. But we, as a research center, we are currently running experimental work to find out what's the source of lithium in New Zealand geothermal brines, so which rocks is it coming from, what minerals. And one of the questions we want to answer is, can we endlessly extract lithium from the brine? So the plan is to reinject in the experimental apparatus back the brine, which is depleted in lithium, and see how much time it takes to re-dissolve into the solution or leach back to the solution the lithium. And if it's even possible at the temperatures where the actual reinjection take place. So we will be able to know if the, for example, 1,000 tons of lithium a year is available only for first year, and the next year is going to be 500 tons, and then the third year only 10 tons, or maybe the reservoir will be quickly filling itself or not. Thank you for this, and I hope that you learned a lot. And if you've got any question, please feel free to ask.
Thank you so much. I believe that Lucjan is with us today, so we have connection through Zoom. If you have any questions, please do not hesitate, and we can ask Lucjan. Lucjan, can you hear us?
Yes, I can.
Hello, thank you again. Thank you for the presentation, for the keynote lecture. Maybe I will have some small question. Actually, we know that the geological conditions in New Zealand are quite different than in our European countries. So my question is about the max depth of your working geothermal wells. What is the situation in New Zealand?
Most of wells are between 800 and maybe up to 2.5 kilometers deep. And it depends, the reinjection wells would be probably deeper than the production wells. But it varies between different parts of top of the volcanic zone.
Are you planning to have some deeper drill holes in the future?
So we do run a huge project of finding the perfect location for well which will hit supercritical conditions, and maybe it's gonna be around 4 kilometers deep or 5. So this is how deep it will probably go, and we want to hit something around 400 degrees Celsius. So we do research, geophysics research on finding the best location, but also experimental work to see what sort of fluid can we expect at these conditions. So yeah, that's in New Zealand we don't need to drill too deep. I can give you an example of in Togo at the lake. They are selling sections just at the beach at the lakefront, and you can drill your own geothermal heating well to heat your house, and at around 6 meters deep you will have already 60 degrees. So we don't really have to drill much. Well, obviously it will depend on location, but it's really hot very quickly.
Thank you so much. It is really interesting for us. We have much different conditions in here. And also at the end, I think you've put really interesting question. What is the lifetime of the lithium? Lithium extraction from the geothermal wells. But I think we will see in the future with the further research. So thank you so much for your presentation, and we will move to the